Chapter 2 is on set theory. In 2.1, we're going to talk about basic set concepts. So we tend to place things in categories, which allows us to order and structure the world. For example, to which populations do you belong? Do you categorize yourself as a college student? What about your gender? What about your academic major or your ethnic background? Mathematicians call such collections sets. A set is a collection of objects whose contents can be clearly determined. The objects in a set are called the elements or members of the set. A set must be well defined, which just means that its contents can be clearly determined. So using this criterion, the collection of actors who have won Academy Awards is a set because we know whether that's a true statement or a false statement. By contrast, we can't consider the collection of great actors because it depends on the person you're asking what would belong in that set. And so we have some different methods for representing sets. So let's consider the days of the week. So the elements would be Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Generally, we use capital letters to name a set. So let's use capital W to represent the set of the days of the week. We have three methods that are common for designating sets. One method is a word description. So we can describe set W as the set of the days of the week. A second method is the roster method. This involves listing the elements of a set inside a pair of braces. The braces at the beginning and end indicate that we're representing a set, and then we use commas to separate the elements of the set. So W would look like Monday, comma Tuesday, comma Wednesday, all the way down to Sunday, and it's wrapped in curly braces. We do not use grouping symbols like parentheses or square brackets to represent sets, and we only use commas to separate the elements of a set. The order in which the elements are listed in a set is not important. So as long as it's listed once in there, then you're good to go. So for example 1, we want to write a word description of the set P equals Washington, Adams, Jefferson, Madison, and Monroe. And so if you're not good at history, like I'm terrible at history, these are the first 5 presidents of the United States. So to write a word description, we'll just say that set P is the set of the first 5 presidents of the United States. So we're just describing what the set is. For example 2, it says set C is the set of US coins with a value of less than $1, and we're using roster method. So that's when we use the curly braces and we list the elements individually. So C is equal to, and we just want to list all of the coins that are less than $1. So we have penny, nickel, we got a dime, a quarter, and a $50. The third method for representing a set is with set builder notation. So using this method, we can write our set of the days of the week as W equals, we still have our curly braces. We put a variable, usually X, and a vertical bar. The vertical bar means such that. And then you write a description using that variable. So X is a day of the week. So before the vertical line is the variable X, which represents an element in general. And then after is the condition X must meet in order to be an element of the set. And so you can see in table 2.1, we have word description, roster, and set builder for the same set, so you can see the difference between the three. So for example number 3, we have A equals the set of all X such that X is a month that begins with the letter M. And we want to write this using roster method. So this is when we have a curly brace and we list them individually. There are only 2 months that have the letter M, and that's going to be March and May. The representation of some sets by the roster method can be rather long or even impossible if we attempt to list every element. So let's consider all the lowercase letters of the English alphabet. Nobody wants to write out all of these. So set builder notation tends to be chosen. And so we'd write L equals the set of all X such that X is a lowercase letter of the English alphabet. If we wrote it in roster method, you can see all of the letters listed below. But we can shorten it by using something called an ellipsis. And that's just 3 dots. So you can see the pattern, and then you want to put the element at the end. So we have A, B, C, D, dot, 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 all the way up till Z. If there's not a last element, you can just use the ellipsis to indicate that it keeps going forever and ever. The next thing we want to do is consider what the empty set is. So let's look at the set X such that X is a fawn that speaks, and X such that X is a number that's greater than 10 and less than 4. Both of these sets contain no elements. There are no fawns that speak except for Bambi. There are no numbers that are both greater than 10 and less than 4 at the same time. And so sets such as these that contain no elements are called the empty set or the null set. And so we can indicate this by an empty pair of curly braces or the null symbol, which is a 0 with a slash through it. You do have to be careful though, because if you put the null symbol inside your braces, that is not the empty set. So which of the following is the empty set? The set of 0. That is not the empty set because it has an element in it. It has 0 in there. What about just 0? This isn't even a set, it's just a number. It doesn't have curly braces around it, so it can't be the empty set. What about X such that X is a number less than 4 or greater than 10? So it can be less than 4 or it can be greater than 10. Well, that has a bunch of numbers in it, so it's not empty. This is not the empty set because it has elements like 2, 3, 11, 12, so on and so forth. And the last one, X such that X is a square with exactly 3 sides. Well, we know that squares have to have 4 sides, so this would be a true statement. There are no squares that have 3 sides. So we have some notations for set membership. So this symbol, it looks like a funky looking E, is used to indicate that an object is an element of a set. And so we just replace the words "is an element of" with this symbol. If we have the same symbol but has a slash through it, then that means it's not an element of the set, and we just use those to replace the words "is not an element of." So we want to know if the following statements are true or false. So is R an element of A, B, C all the way up until Z? Well, yes, R is a letter in the alphabet, so this is true. Seven is not an element of 1, 2, 3, 4, 5. That is also true because 7 is not in that list of elements of our set. What about the set of A is an element of AB? Now this is false because with the curly braces, this is now a set, and that set is not an element. The next set we want to talk about is the set of natural numbers. So the numbers we use for counting, or the first set of numbers you learn as a kid, 1, 2, 3, 4, 5, 6, 7, forever and ever, we call these the natural numbers, and it has this bold-faced letter N. That's another way to represent it. And so we want to express each of the following sets using the roster method. Set A is the set of natural numbers less than 5. So what numbers are less than 5? That would be 1, 2, 3, and 4. Set B is the set of natural numbers greater than or equal to 25. So because it's equal to 25, that's where we need to start, but it keeps going forever and ever. And so to indicate that, you just do some ellipses at the end. And set E is the set of all x such that x is in the natural numbers and x is even. So my even numbers would be 2, 4, 6, 8, and again we're going to use those ellipses or the dot dot dots to indicate it keeps going in the same pattern forever and ever. So in table 2.2 you can see some different inequality notations in the sets. So if x is less than a or less than a number, we can write that as an example in set builder notation, and then we can also write it in roster method. If I add the bar underneath that less than symbol, it now means it's equal to that number. So instead of just having 1, 2, 3, I have to have 1, 2, 3, 4. Same thing goes for greater than, or greater than and equal to. So if I look at greater than 4, we have to have 5, 6, 7, 8, but greater than or equal to 4 is now 4, 5, 6, 7, 8. And then for x being in between two numbers, with both of them strictly less than, then I don't include my boundary numbers. So if I'm looking between 4 and 8, it would just be 5, 6, and 7. If both of them have the bar underneath, then I need to include both of my boundary points. So 4, 5, 6, 7, and 8. And if only one of them has it, then you will only include that specific number and not the other. So let's express each of the following using roster method. So x such that x is in the natural numbers and it's less than or equal to 100. So that means we're getting up to 100. So that's 1, 2, 3, ... You could do 98, 99, and 100. The set of all x, such that x is in the natural numbers, and 70 is less than or equal to x, which is strictly less than 100. So we are starting at 70, and we keep going up. We got some ... and then we go to 98, and 99 would be the last number because it doesn't include that 100. Now let's talk about cardinality and equivalent sets. So the number of elements in a set is called the cardinal number or the cardinality of the set. So we don't care about what the set looks like, we just care about how many elements are in it. And so if I look at the set of our vowels, A, E, I, O, and U, that contains 5 elements, which means it has a cardinal number of 5. So the cardinal number of a set A, represented by n of A, is the number of distinct elements in a set. And so the distinct part is very important, which means they have to be different. So repeating elements in a set neither adds new elements to the set nor changes its cardinality. So if you have a repeat of a number, you don't count that in the cardinal number. So let's find the cardinal number of each of the following sets. A equals 7, 9, 11, and 13. So the cardinal number of A would be 4 because we have 4 different elements in our set. A set of B is equal to 0. This has 1 element, so its cardinal number is 1. For set C, we have 13 through 23. So the cardinal number of it is 11 because we have 11 elements from 13 to 23. And the last one is the null set. Well, by definition, the null set means it has no elements in it, so its cardinal number is 0. And so sets that contain the same number of elements are said to be equivalent. So set A is equivalent to set B, means that they have the exact same number of elements or their cardinal number is the same. They don't have to look the same at all, they just have to have the same amount of elements, which makes them equivalent. And so if they're equivalent, we say they have a 1-to-1 correspondence. So the graph below shows the top 5 impediments to academic performance for U.S. college students. Let set A be the set of 5 impediments, and let set B be the set of the percentage of college students reporting each impediment. Are these equivalent? So let's write down set A. Set A is our 5 impediments. So stress, sleep problems, illness, anxiety, and work. Set B is those percentages that are listed above the bars. So we've got 28, we've got 20, we have 19, but it's twice, and so we only need to list it once. And we've got 14. And so the cardinal number of A is 5. And the cardinal number of B is 4. So because 5 does not equal 4, these sets are not equivalent. So finite sets and infinite sets. If a set A is finite, if the cardinality is 0, aka A is the empty set, or it's a natural number. If it's not 0 or a natural number, then it's an infinite set. So if we can count the cardinality, then it's finite. If we cannot count the cardinality, it is infinite. So an infinite set would be the set of all natural numbers. 1, 2, 3, 4, 5, and it keeps going forever and ever. For sets to be equal, that means that set A and set B contain the exact same elements regardless of order or possible repetition. We symbolize those by just using an equal sign. So if A is WXYZ and B is ZYWX, then these are equal because they contain the same elements even if they are in a different order. So if two sets are equal, then they automatically are equivalent because they have to contain the same number of elements if they contain the same exact elements. So we want to know if these are true or false. 489 equals 894. That's true because they contain the same elements even though they're in a different order. 135 equals 0135. This is false since 0 is in the second one and not the first.